Good afternoon everybody. Today we will discuss the different aspect of the finite element method. Last class what we discussed that we develop the stress analysis model, the relation of the stiffness matrix, the formation of the stiffness matrix for a particular element, and we can see all that stress analysis part. We normally use the constitutive relation between the stress versus strain and the strain versus displacement. So, we use some relation, and by following the potential energy minimization we finally develop the formulation of we bring the stiffness matrix and we solve for displacement field. So, that was the general approach in case of the stress analysis model, but in any kind of the physical process, or maybe that can govern some kind of the physical law also. For example, it is a heat transfer problem in any kind of the manufacturing process that it may associate with some kind of the heat transfer. So, once we looking into the heat transfer, or we are interested to know what is the temperature distribution, then we should know what are the governing laws or what are the governing equation basically drives this kind of the physical mechanism, or maybe that is why when any particular we try to solve in general the heat transfer problem. So, associated with the boundary interaction or boundary condition, then governing equation along with the boundary condition, there is a need to look into the some techniques. So, that means we normally use the weighted residue technique to find the finite element based formulation. So, today we will discuss that part, how we can using the weighted residue technique we can do finite element based formulation in the cases where there is a governing equation is there, as well as the mathematical interpretation of the boundary condition is also there. So, in that case we will look into that how the finite element formulation can be done, but before that what is the weighted residual method or weighted residue technique we normally use in any kind of the finite element formulation. Suppose the governing equation and boundary condition represented by these two different form of the equation. So, equation 1 we can see that A, the equation, the functional form of a governing equation in general, and equation B, that is a functional form of a boundary condition, and both as a function of the T is the basically the solution variable. We can say, for example, heat transfer problem, it is equivalent to the temperature. So, once we get these two equation, what is the governing equation, what is the boundary condition for this particular problem, then we assume that some arbitrary temperature distribution in for example, in this case we assume some arbitrary temperature distribution in the domain, and that arbitrary temperature distribution we consider as a solution of this particular equation, by assuming that if it is substituted in this equation, this particular equation in this case it is equation 1, then this equation will not be satisfied, may not be satisfied also, because in this case we do not know the exact solution, we are assuming some arbitrary solution, and then that arbitrary solution we are feeding to the equation, we are just trying to fitting this arbitrary solution equation. It is not necessary it will satisfy this particular equation. So, therefore, in the mathematical form we can write the obtained results once we we assume this particular solution of this equation, then put this mathematical form of the equation, we can see that A T dot we assuming this is the solution of this particular equation. So, it should satisfy then B is this boundary condition, and it is the solution is the T dot. So, then both should satisfy if it is the exact solution, but we do not know the beforehand, we assuming some solution, that is why it may not satisfy. So, once we put this thing, there exists some sort of the residuals. So, that is the quantities called R1 and R2 residuals, and in the mathematical form it is not equal to 0, that means some residuals are there, that means definitely it is not equal to 0. If it is equal to 0, then our assumption was correct and we are getting the solution of this equation by assuming this particular solution, but it is not possible to get this solution in general. So, there we arbitrarily by assuming some arbitrary solution, if we want to satisfy this particular equation, there must be some amount of the residuals must be there, and that residuals can be represented this way R1 R2. So, then this equation 2 is represented like that. Other way also, if you look into this figure 1, that arbitrary points within the domain. So, that so many arbitrary points are there 1, 2, 3, 4 up to dot n. So, this residue R1 will different. So, that means that different at the different points, R1 value can be different at the different points shown in the figure, whereas the residue R2 will vary on the boundary points. Actually, the R1 the residue is defined within the domain, but R2 is just the residue existence of because on the boundary. So, therefore, R2 will vary on the boundary points. So, but it is not necessary R1 can be fixed value. So, R1 can vary, the residue can vary at the different points. So, even we are talking from the point of the finite element based method, because in finite element what we do, we just discretize the domain. Discretize the domain means we create the elements, small elements within this particular solution domain, and we are trying to look into what is happening looking into the residual in the particular node point. So, that is why different point 1, 2, 3 is the domain, that we assume that we can it indicates the kind of the node point in this domain, and we are trying to satisfy this equation with the particular we are defining the equation in the node points, and based on that we can say that when you try to satisfying some arbitrary solution of this particular equation, then we feed the value looking into what are the values or looking into what are the residuals is exactly on the different node points. Now, this T dot we are assuming T dot is a arbitrary solution for this particular equation, Governing equation and boundary condition as well. So, T dot to be the solution. So, that means T dot to be the solution of this governing equation. So, then if it is not T dot is exactly the solution of this governing equation, then definitely there may not be any kind of the residual. So, residue should be 0. So, then in that cases residue should be 0. If T dot is exactly satisfying this equation and in each and every node point, then that is the exact solution. It is possible to that we consider this T dot is the solution of this particular equation. Otherwise, there exists some sort of the residuals. So, from that concept we can finally analyze these things. So, now to understand these things, how this residual weighted residue technique works on, that we assume some one dimensional domain extending from point A to and point B. We can see that one dimensional domain, and this is x direction one dimensional domain, and a T dot is this functional form, T dot is the solution in this particular case, and W is the weighted residue and weighting function, and this we discretize this domain in the different thing, or maybe that small elements. So, it is a one dimensional element such that we consider what is this discrete point as basically node point. We are looking into the solution, or we are looking into the residuals for this particular equation. Now, if the distribution of the residue, then we distribution of the residue means in the discrete point what are the value of the residue, and this distribution we consider for some arbitrary temperature distribution T dot is given by A T dot. That means, this functional form A T dot, the particular distribution of the T dot or functional form of this A T dot, we are assuming this is the solution of this equation. Then we consider the another function. So, in that case we introduce the another function W, which is called the weighting function. Now, this function W is chosen in such a way that when A T dot, that means this is the T dot is the solution for the particular equation, and W is the another function if we consider, and the W is the multiplied at every point and added, we obtain the quantity. So, integration of this thing A to B, but in this case this is the weighting function, and this is the actual, assuming the T dot is the solution, arbitrary solution of this governing equation, and this is the functional form of the A T dot. So, this weighting function and multiply this A T dot, and this is one dimensional problem. So, only the variation along x axis. So, therefore, dx integrand of this we can add this quantity, we can represent this thing. So, this where W is the also arbitrary function, that weighting arbitrary function, it is called the weighting function. So, W is called the weighting function. So, to satisfy this the solution, or to bring some kind of the solution of a particular equation, we just multiply with another arbitrary function, that is called the weighting function, and in the form of a integral this thing, but definitely this we are integration, but this integral form is defined, or maybe we can look into the numerical integration of this thing. So, in that integral form we can represent this multiplying the weighting function and the actual governing equation. For that governing equation we are assuming some solution, arbitrary solution, then A T dot will not be 0 at all the points, definitely that this functional from A t dot, the A t dot is basically it is in, if you look into the analytical solution, it follows some kind of the distribution or some functional from it follow. So, therefore, A t dot will not be 0 at all the points for a distribution of t dot, which is not solution of the problem. So, if A t dot is 0 each and every point, that means each and every node, we looking into for one dimensional problem, each and every node point, if it is equal to 0, then this is the solution, but if it is not equal to 0, then this is not the solution of this particular equation. So, therefore, the possibility of the above integral being 0 is minimal. So, the chances is very minimum to that being the 0 of being the 0 is the minimal. So, that is why we multiply this thing, the weighting function in the form of integral. Now, if we consider several arbitrary distribution of the weighting function w, so different form of the w, several arbitrary different types of the different functional form of the weighting function w1, w2 or maybe different weighting function at the different discrete points. If we consider and obtain a distribution of the t which makes this integral 0 for all values of w, then only the possibility is in which this can happen when the t is the desired solution of the problem. It means that in other way you can see that define, and if it is equal to 0, then it indicates that it means that the by putting the weighting function, we choose the weighting function in such a way that it becomes 0, then we can say that t dot is the solution of this particular problem. So, we will looking into this thing desired solution t dot, it is the desired solution of this particular problem, and we assume that t is the desired solution of the particular problem. The other way also. So, whatever functional form we can see that solution of this particular equation, and this we can obtain with the multiplying of the different weighting function. So, therefore, thus the condition for temperature distribution. So, basically we are looking for the temperature distribution T, that distribution to be the solution stated in the form of the expression of 1, expression of the equation 1. We can look back to the equation 1 also, that this is the expression of the. So, this A T equal to 0, when T will be the solution of this particular temperature distribution if, get the T solution if this is the, this multiply by the weighting function W1, but this equation 1 means both are when you are talking this kind of problem, both it is important to consider the governing equation in the domain of the solution domain as well as the what are the boundary condition is important, and combined together we can define the in a particular problem. So, that means we are giving some weightage or weighting function, introduce some weighting function which is multiplied by the governing equation, and this since the governing equation is valid over the volume, over the domain, then whole domain, that means over the volume. So, that is why we put the dv plus integration, we put the another weighting function W2. It is not necessary weighting function can be same also, can be different also, but that different weighting function if we consider W2, and Bt represents the boundary condition. So, that means it is a boundary interaction. So, which is defined over the surface, because boundary is represented 3 dimensional problem, boundary is represented over the surface. So, then this weighting function into this boundary condition, mathematical form of the boundary condition, assuming that T is the solution and what is satisfied, this should equal to 0. It means once this satisfying a condition, this particular condition equal to 0, then we can say that T, from this expression we can get that T is the solution, that means temperature distribution in this case is the solution for this particular problem. So, that other way we just in this case, so W1 and W2 comprise of the many sets of arbitrary weighting functions. So, there are so many possibilities of defining the what is the W1 and W2, or both can be the same also. But finally, in mathematical form, when you multiplying the governing equation boundary condition with some weighting function, doing the integration which is integrated over the volume for the governing equation and integrated over the surface area for the boundary interaction, then the whole system equal to 0. Then you can assume the by solution of this equation is the from here what is the temperature distribution, that is the solution of this particular problem. So, in the other way, by introducing the weighting function, we can form the mathematical form of a any particular problem, and which is basically looking into that particular problem, and then we can formulate the using the finite element method any kind of the problem which is governed by the one particular governing equation and along with the boundary interaction or boundary condition. Now, we can see W and W2 maybe have different sets or different weighting function. There are so many possibilities are there for W1 and W2. How? Looking into that, the so many possibilities of W1, W2, and I think that is not discussion what are the mathematical aspect, what are the different forms of the weighting function, and then what are the limitation and all these things, and how we can form this weighting function. That is not beyond the scope of this particular course. Rather, we can focus on the very simplified way to understand the concept of the weighted residue technique in this particular case, and then how this what we can put the weighting and more in the to can define the heat transfer problem associated with the welding process. That is the focus of this particular course. So, therefore, based on the selection of the weighting function and there may be different techniques, weighted residual method can be divided into 5 categories. So, you can see there are in general there are 5 categories problem can be defined based on the different nature of the weighting function. So, one is the collocation method. Collocation method, the weighting function is chosen from the family of the direct delta function in the domain. So, it is basically simply in general sense we can say that this method is basically the particular weighting function we can choose, and accordingly this method has been developed, or this method is normally used to get the desired finite element based equation, or maybe to defining the problem using some governing equation and boundary condition. Similarly, subdomain method is simply some modification of the collocation method is required in this particular cases. Even least square methods also, in this case the summation of the all the square residuals. So, we estimate the residuals. So, summation of the all the residuals, that means putting the weighting function for a particular node point and this governing equation, we can assume some solution, then multiply this thing, summation of this thing all the residuals, and square root maybe summation of all the residuals and square of them can be minimized to get the finite element formulation for this using this least square method. So, that is the methodology is beyond our scope of analysis in this particular course. Then Galerkin method. So, Galerkin method basically we will be discussing and will be for this particular courses, and based on this Galerkin method what we can develop the different finite element formulation of the associated welding process, and that is the main focus of this course. We will discuss later on this thing. Then method of movements, in this cases the weight function are chosen from the family of the polynomials. So, from the family of the polynomials the weighting function can be chosen, and based on that the method of movements techniques has been developed. So, we can see that all this methodology and weighted residue technique in general sense we can say that how we can choose the this thing, how we can choose the weighting function and what we can minimize the residuals, and based on that the different methodology, different techniques of the finite element formulation has been developed. Now, let us look into what is the Galerkin method which we are supposed to use in this particular course. Now, condition weighted residual method, condition of a function to be used as a weighting function. Two things are there, two conditions are there, that what are the as a which functional form can be used as a weighting function. One is the first point is the all functions should be totally independent. We have to choose the weighting function in such a way that all the functions should be totally independent. And second thing is that the function should be very simple. So, in order to avoid any kind of the computational difficulty. So, it is a definitely there are lots of possibilities to choose the different form of the functional form, but is as simple as possible other such that we can avoid some kind of the computational difficulties. So, this case you can see the figure. Before going into the details of this analysis, we should understand these things in a particular 1D element, and suppose there are n nodes and there are so many elements n minus, I think if there are n nodes, I think there are n minus 1 elements will be there, are each separated, it is separate elements. So, that means this is the node number 1, 2, 1 and 3, node number 4, 5, 6, 7, 8, 9 like that, 10 like that. These are the different node numbers and this is the node number n, particular n number. Now, 1, 2, this indicates the one element in a one dimensional problem. Similarly, 2, 3 is another element, 3, 4 is another element like that. So, this way we can define the different elements nodes also in a one dimensional problem. But you can show the variation of shape function we have seen, we have already discussed that shape function value, even if we look into the expression of the shape function in the that we can see that shape function from one particular associated with node 1. So, we can use the several shape function n1, n2, something like that. For a particular element we use the different shape function. So, if one element they are having the tetrahedron element, in that cases there are 4 nodes. So, we can find out that there are 4 shape function n1, n2, n3 and n4, that we have already discussed in the last class also. Now, in this case we can assume there is a one element and there is a node one element have associated with the 2 nodes n1 and n2. But on the particular case, this if it is a n3, that node n3 value of the shape function will be 1 for this particular node, but its 0 corresponds to the other surrounding 0. So, therefore, n1, n2, nn are the nodal shape function. So, that is why this shape function we can say the nodal shape function, because we are n1 which basically 1 is the node number. So, accordingly we can define the shape function also. So, n1, n2, n3 this all represents the, these are the nodal shape function. Now, we will see how it works in this case. Now, nodal shape function has the elements at a particular node, definitely nodal shape function is a particular node and the adjoining elements. So, one particular node and the element. For example, in this case this is the particular node n3 equal to 1, but adjacent elements for these cases are the adjacent node 2, 3 and adjacent element 3, 4. At the node value at 4, basically node point 4 equal to 0 for this particular case, shape function will be 0. So, the value of the nodal shape function is 1 at a particular node and its value is 0 at every other node. So, we can see that for the particular n3 value, n3 equal to 1 for this particular node, but it is 0, the shape function, the nodal shape function value equal to 0 for other nodes. That is very obvious also. Now, if this shape function can be used as a weighting function, then this approach is called the Galerkin method. That is true if this shape function are used as a weighting function. For example, we have seen that when you try to establish the weighted residue technique, we have to choose some weighting function. So, particularly the Galerkin weighted residue technique, that means in Galerkin method we normally use the weighting function as a shape function. Same shape function if we use, then this approach is normally called the Galerkin approach. So, the weighting function is the same as the shape function. For example, in this case if we consider the one weighting function associated with the governing equation as a ni. So, ni is the weighting function is the ni, I indicates the 1 to n, it basically indicates the node, point. Now, W2, that means another weighting function, it can be used the also minus ni. So, if we consider the governing equation in such a way that it is a plus ni, that means shape function. Similarly, weighting function W2 can be considered as a minus ni. So, ni corresponds to the basically the nodal shape function for each and every node point, particular node point. Thus, the weighted residual statement is given, equation becomes that if you see that this is the weighting function and this is also weighting function. So, this weighting function W2 he consider the minus ni. So, simply put the ni here, and this is the governing equation, this is the boundary condition, and because it is defined over the surface and this is defined over the volume. So, multiply by the shape function and this equal to 0. In this case, once we establish this equation and in the integral form, it means that once we get the solution, if we find out what is the temperature distribution from here, then that indicates the solution of this particular problem, or we can say this is the solution of this particular problem by just putting in the weighting function. So, that is the importance of the putting some kind of the weighting function in a finite element analysis. Now, look into this particular problem, the heat conduction analysis. So, we assume the steady state heat conduction equation. You know the steady state heat conduction equation and K K into del T by del X, this thing Q dot and the I think equal to rho Cp del T by T. So, basically this term equal to 0. So, then there is no time component here in this particular governing equation. So, we can say this is a steady state equation, just simply neglecting or maybe make it equal to 0, because temperature variation is not independent of the time component. So, that is why it becomes the steady state heat conduction equation. So, this is the steady state equation, and it is also the XYZ, that means we can say that it is a 3 dimensional steady state heat conduction equation, where Q dot is the rate of internal heat generation per unit volume. So, this equation, what we can see that how this is, we assume this is the governing equation any kind of the heat transfer problem. It can be associated with the welding, any manufacturing process, or it can be associated with the some other problem also, but in general this is, there is a heat transfer problem, we consider the Fourier heat conduction equation or 3 dimensional heat conduction equation in the steady state condition. But the boundary condition specified at the surface. So, that means in a welding problem we can see the boundary condition. So, suppose this is the domain, and we have seen the boundary condition in a welding problem also, it is as in general the heat is conducted on the surface, that indicates the K into del T by del N, that normal to N equal to N vector represents the normal to the surface. So, it is defined on the exactly the heat conduction, but that is defined exactly on the surface. Alpha T is basically maybe heat loss by convection and radiation from here, and maybe other surfaces, and the Q is the basically heat flux. The impose, there may be some in particular problem, there may be the heat is applied, heat flux is applied to the surface, and that is the Q in general. So, Q is the heat input to the surface, and in general I am talking about, and alpha T is the heat loss, the H equal to the heat loss by convection per unit area T minus T ambient temperature. So, basically H T in general, alpha T we can say in the generalized form, that alpha T is the variable in this case. So, therefore, it is a general form of the boundary interaction normally associated with the heat conduction problem, if we assume that, and that is defined only on the surface S1. So, let us see, let us look into this, all this defined over the surface S1 and this boundary interaction. Now, S1 represents the portion of the boundary on which boundary conditions are specified. So, it is not necessary the whole boundary is subject to some sort of the boundary interaction. So, it is a particular boundary interaction may be possible, even some other boundary condition can be imposed in the other part of the boundary. So, we are assuming the it is a small part of the boundary, this boundary condition in general form of the boundary condition is there. So, therefore, we can see this is the governing equation, this is the boundary condition. So, from here what we can develop the using the application of the Galerkin-Waite residue technique, and we can formulate the heat transfer problem. Now, considering AT, if you remember equation 1, AT is the governing equation, and BT we consider the boundary condition, the T is the functional form, T is the as a function of T, we can say like that, as a function of T means as a function of temperature, this is the functional form. As the boundary equation in equation 4, and applying the concept of the weighted residual method to the 3 dimensional steady state heat transfer problem. So, 3 dimensional heat transfer problem. So, this is the, if you see that AT, this weighting function Ni, other is the Bt and weighting function Ni, and this is the plus, and this is over volume over surface, and this is dV, it is ds. Same way we have considered. So, this is the governing equation up to Q dot, this third bracket, within the third bracket Ni is the weighting function as the same as shape function over the volume, integrand over the volume, and this is the integration over this volume, the volume integral. So, now similarly for boundary interaction, this is the Bt in this case, and this was At this case, and this is the Bt, and this is the shape function surface, because boundary interaction over the surface, and minus shape function we have defined, if it is a plus for the governing equation, the minus for the boundary interaction. So, this becomes 0. Now, this is the formulation, this thing, in that cases the what are the temperature distribution we will be getting, then this is the solution of this particular equation, and of course, in this case we are using the following the weighted residue technique. Now, this look into the individual elements for this particular equation. So, this can be represented also, this equation can be represented also into T, the differentiation del to T gradient. If you look into the gradient divergence curl in the vector form, we can represent this second del to T by del x square plus del to T by del y square, just simply represented by this equation can be written in general to T. So, that is T is the governing equation here. Now, K we just keep it outside K, so we are assuming this in K, the thing Ni is the variable and dV is the volume over the volume. Second term, this Q dot term, Q Ni Q dot dV over the volume, this without expanding this different elements of this particular integral. Then N K, K is the, this is the from boundary interaction Ni del T by del N into ds. Second term is coming like this, Ni alpha T ds over the surface. Third term it comes like that, it is also Ni Q ds, this is also over the surface. So, from here now we apply first form of the Green's theorem. So, Green's theorem is simply we can use the relation from the volume integral to the surface integral in that formula. From here you can see that we apply the Green's theorem here, because in this case from this term we can use the Green's theorem. So, this term is equivalent to this term, okay. And then from here we can see that this Green's theorem over the volume integral to conversion from volume integral to the surface integral. So, if we apply the Green's theorem here, then this part will come to this side, but it will be negative sign, and the another surface components will be there, another this is if you see over the volume. So, this is volumetric component will be there, on the surface components will be there if we apply the Green's theorem for this particular part. Now, see from here we can expand by Green's theorem, that two terms will be there. So, this will come other side, then this term will be there as well as this surface term and this volume term will be there. Now, looking into this equation how this can form, then this terminology, the first term from here we can convert into this term. So, this term represent that, here you can see minus k del Ni by del x, del T by del x, del N by del y, del T by del y, these terms will be coming into the picture dV. And another application of the Green's theorem also we can find out this, this is other surface term will also be there. So, u is equivalent to here we can see the shape function, and u is equivalent to here shape function, and phi is basically u is basically equivalent to the shape function Ni, and phi is equivalent to basically temperature T here. So, Ni and T, in terms of that we can find out k del Ni by del x. So, this is in the gradient basically del, this indicates the, sorry, this is the u, it indicates the gradient of u, or we can in this case the gradient of u means here Ni. So, gradient of Ni, and gradient we can see the gradient is basically del by del x I, this is a vector quantity, del by del y j plus del by del z k. So, from here the gradient of that it represents the, this indicates that two gradient is there, and gradient of phi. So, in this case gradient phi means is the, it will be simply the phi is represented by T, basically the T, and then dot product of that indicates that del Ni by del x, the first term, del T by del x, del Ni by del y, del T by del y, del Ni by del z, del T by del z. So, this is the first term is coming into this picture over the dV, and second another surface terminology will be coming, that plus this is the k Ni del T by del N, k we assume is a constant this thing. So, del Ni or other parameters are variable, del T by del N del S. So, then it is coming from the from here this term, this term will be coming, the surface term, surface integral term will become into the picture. U is equivalent to the t here, u is equivalent to shape function ni, and phi is equivalent to t. So, del the gradient of phi means gradient of t, in this case phi equivalent to t. So, therefore, we will be getting this expression k ni del t by del n into ds. So, this why del t by del n, because we define the surface means, but we defining del t by del n, that means this temperature gradient which is defined normal to the surface. So, del t by del n into dx, this term is coming after the conversation from the volume integral to the surface integral. Now, look into the other term, this is already was there, and this is from the surface term and already from the boundary condition there. Now, next line, this term from the, this comes from the Goulburn equation and this term from the Goulburn equation by applying the Green's theorem, but this terms from the boundary condition. So, that will balance if we look into this thing. So, finally, the expression is like that, dV ni this one ni equal to 0. So, therefore, on discretizing the domain into the 4 noded. So, these are the different terminology we can use, and this kind of expression we reach after the application of the Galerkin weighted residue technique. So, on discretizing the, now it is necessary to discretize the domain 4 noded. Now, this is the general form of the equation. Now, depending upon the ni, what should be the value of I? It depends on the what kind of the element, how many nodes are there in a particular element, that has to be. For example, if it is the 4 noded tetrahedron elements, 4 noded tetrahedron elements I can vary from 1 to 4, but if it is a brick element, then I can vary from 1 to 8. So, depending upon the what kind of the element we consider, or you have discretized the domain, accordingly I can vary. So, therefore, if we assuming that on discretizing the domain into 4 noded tetrahedron elements, then the temperature within particular element can be written like that. So, temperature variable here T, expression in the temperature T itself within the, in the form of a nodal temperature as well as the shape function form. So, that NiTi summation of I equal to 1 to 4, which is also equal to the shape function into T, that we have already seen, that even we have shown in case of the displacement field also. If you remember correctly in the stress analysis part, there we have developed that we have seen that displacement field can be represented in the form of a nodal value. So, T in this cases also temperature can also be represented in the form of, this is the shape function and this is the in the form of a nodal temperature value. So, T. So, in that form we can represent. So, but in this case assuming that n is the variable quantity. So, whatever variable quantity means, we can do the derivative, first order derivative, it can be if it is a linear shape function, if you do the first order derivative then it becomes constant also. The T is the nodal temperature, we can assume this is a nodal value. So, therefore, the volume integrals and the surface integrals of the last equation, equation 8 are expressed at the sum of the over all the elements. So, once we do all this term, this in this particular expression here, we can discretize, we can do integrand, but integration we can perform over the numerical integration, then we can perform for a particular element. Then once we get the particular value of the particular element, we can distribute the value in the each and node point, but once we assemble for the contribution for the all elements, then accordingly we can put the their nodal value, which point the node point is common 1, 2 or 4 different element. So, we keep on adding the contribution, basically we calculate all these things one particular element, then we call one by one element and accordingly we can put the position of the particular node point, because one particular node point may be the common node point, may more than one or more than one elements in that particular case. So, once we call the particular element, what is the contribution for the node point, and then when you consider other element and both the element having some common node point, then we just keep on adding for this particular common node point, and in that way we can form the contribution for the each and every node point, and we form the linear system of equation, or we can say the form of the matrix, that size is normally that number of depends on the number of nodes. If there is n number of nodes, the size of the matrix Ax equal to size of the matrix, we can see that Ax equal to B, that is the final form of the equation. So, A matrix, if there is n nodes, the A can be n into n node, but This calculation we can do for particular element, and then we call all the element, and in a form that we make the assemble on big matrix A, which is dimension of this matrix is the n by n, it depends on the number of nodes in this particular domain. Then we solve for the equation. Therefore, if there exist n nodes within the volume, so there will be n unknown temperatures, definitely each and every nodes are there. So, each and every node point the temperature can be considered as an unknown quantity, and that is temperature can be considered the Ti. So, where I can vary from 1 to n in that particular equation 8. Then to obtain the Ti values, that means Ti equal to 1 to n, n is the number of nodes. So, in that cases n by n matrix has to be solved equation. So, we can get the n number of equations and n number of variables. So, in that case we can solve this equation and the simultaneously solve for the values. So, in that cases we will be able to find out what is the value of the temperature for each and every node point. So, therefore, the equations can be obtained by considering the n separate values of the weighting function Ni, each n value giving a separate equation. So, that is also possible, the equation can be obtained considering the n separate values of the weighting function, that is also possible. In this case the weighting function is equal to Ni, that each n value giving the one separate equation. So, if the number of nodes is n, then the number of n by Ni values will be the n. So, Ni also value it can be also n1 to n. So, n1, n2, n3 that up to n. So, that are the different shape function we will be able to feed in this particular case, and then we will be able to solve this particular problem. Therefore, equation 8 can be expressed like that, contributing from all the elements. Then we can find out the V E element for this we expressed is first we estimate for a one element, and we assuming the one element having the 4 nodes. So, contribution from the 4 nodes, or in general one element we can form this matrix first, and then we assemble for the all the elements. So, the summation of the all the elements. So, same way it can be done for other cases also, volume in this can be the surface over the surface, and all these thing the different contributions. So, therefore, we have the m elements of which r elements have boundary domain as their face. So, if we look into have to be look into that whether this element, the one particular component of this particular expression of finite element formulation, this part that whether it is defined over the volume or it is defined over the surface. So, contribution from the surface boundary condition, that is over the surface. So, in that cases this particular heat interaction with the boundary, the which part of the boundary is basically, or how many number of elements is associated with this particular, that has to be taken care of. For example, in this case r number of elements exactly on the boundary, which is maybe interaction through the boundary. So, therefore, r can be different as compared to the m. M is defined for the whole domain, total number of elements. So, then NIQ over the domain. So, that is how we consider the m in these cases, the whole number of elements of the whole domain having total m number of elements. So, accordingly contribution can be considered, summation can be considered from equal to 1 to m. Here contribution from 1 to r, contribution from 1, because r is the number of boundary elements which is boundary interaction is basically happening in this particular case. Now, considering a tetrahedron mesh that has only 4 nodes. So, therefore, only 4 non-zero values of Ni will exist for a particular element. Definitely in a tetrahedron elements mesh that are only 4 nodes. So, therefore, 4 non-zero values of Ni will exist for an element. So, basically one particular element, one is from this, the interaction from the each and every node to other node within element will be 4, because there are 4 number of nodes one particular element, and particular in case of tetrahedron mesh. Therefore, element will contribute terms only in 4 equations of a set and of a n equation expressed in equation 10. So, therefore, element will contribute terms only the 4 equations. So, therefore, we count the m of, although we are doing the summation for a equal to 1 to m. So, total m number of elements, but nodes number are different. Its node number is not equal to the element number. So, node numbers can be different as compared to the node number. So, once we assemble this thing, so accordingly the node tracking of the node numbering is also there in their particular domain, such that finally we will be able to find out what is the temperature of each and every node point. So, that is the node point. So, that is the dimension of the equation in such a way that it depends on the what is the total number of nodes, not total number of elements in this particular case. Now, this expression you have already seen the temperature variable can be expressed as shape function into T, the nodal temperature, or summation of I equal to 1:4 Ni Ti, depend I equal to 4 up to 4, because it is a tetrahedron element. If it is weak element, then 4 can be replaced by the 8, number 8. So, now look into this thing. If 4 nodes associated with the particular element E and these are designated as 1, 2, 3, 4 for the simplicity, the corresponding term wise contribution for this element, looking contribution from this element for the more explore this particular part, how the formulation can be done. So, if you look into there are 4 node on a particular element. So, term can be represented like that, delta n1, this n is the shape function, because this if you see due to the del t by del x, that was the term actually. So, t we represent t equal to the shape function into nodal temperature. So, then we can say that del t by del x can be like that del n, because n is the variable in terms of n. We remember that when we express the shape function, n can be represented in the form of x, y, z. If it is 3 dimensional, 2 dimensional, depending upon 3 dimensional, 2 dimensional problem, n can be expressed in terms of the coordinates and the as a variable x, y, and z. So, therefore, it can be derivation can be possible here, and in this case equal to T e. So, from that sense it is coming del t by del x is replaced by this value. Similarly, for this thing n 1, and this is for the del n 1 by del z. All these cases we can see, but in same way, that is the node 1. So, if it then is a change in the node 2, then n 2 will come, node 3 n 3 will be coming, node 4 n 4 will be coming. If it is a 8 node, then n 5, n 6, n 7 up to n 8 will be there. So, that needs to be accounting, look into this thing. So, all terminology first term we can explore further looking into all these components. Therefore, the terms T e are nodal temperature, that we have already explained this thing, that do not vary within the element. So, nodal temperature does not vary within the element. So, that is why we consider this as a constant, but n shape function we are assuming it is a variable. So, therefore, this vector is taken out of the integral sign, that is true sign, and rearranging the remaining terms we obtain the elemental contribution in the matrix form like that. So, therefore, rearranging all these things, we can see that looking into this thing, H 11, H 12 term will be there, H 13 and contribution these things 14, 21, 22, 23, 24. So, basically the arrangement. So, it is interaction between the node 1 to node 4. So, different way if you can see the interaction between node 1 within the one element, the interaction between 1 1, 1 2, 1 3 like that, 1 4, similarly 2 1, 2 2, 2 3, 2 4. And the 4 1, 4 2, 4 3, 4 like that, there is interaction, and each term can be like that, H 11, H 12 this way, and all this contribution from the E indicates the elemental form. And finally, this T 1 is the basically that tetrahedron element, that is the having the 4 node. So, therefore, the nodal temperature and 4 node is T 1, T 2, T 3 and T 4, and in general we can say that H e and the T is the nodal temperature in that form. But the general expression for H I j equal to the integration over the V e k del n I del n j del x m, but in these cases m equal to 1 to 3, that means and I equal to 1 2 3 4 in this particular case. So, that means H 11 I can say that H 11 E can be like that, V e and then k del n 1 del n 1 by del x m 1 x 1, or x 1 means x 1 means x, x 2 means y direction, x 3 means z direction. So, that is why this formulation can be formed also. So, in j equal to 1 in this case 1 1, similarly 1 2 1 3 like that, it can be represented in this way also in general. So, I think we can see this part also here. So, 1 1, 1 2, 1 3, 1 4 like that, 1 1, So, that is way we can represent in general way, but remember the bottom side is either combination of the 1 1 1 2 1 3. So, this is the general expression, but this one find out this thing, there is a need to do the integration. So, over the volume integration, but the numerical integration is actually required in this particular problem. We will maybe next time we will show how we can do the numerical integration, or one particular form of the element, how we can form this, how we can form one particular element of this matrix in any kind of the problem. Specifically, I try to explain in the heat transfer problem how this one element is formed. Now, for the second term also we can see that the FQI, similarly this expression can be represented like that, but third and fourth term also can be represented in generally HETE, or you can see that FQ, that means it is a expression. See, this is all these cases is basically required to do some kind of the either integration over the surface or integration over the volume, but all these cases we can do the numerical integration this thing, but how we can do the numerical integration we can show in the other lectures also. So, therefore, total contribution in the matrix form can be write that HE, this part, this is also part, and this is the load part. So, that in the with the application of the Galerkin weighted residue technique, and in these cases we using the weighting function same as the shape function, and from that shape function we can form the matrix form of a particular equation. So, definitely with the weighting function all this application, all this thing is required once we try to do the analysis the any kind of the problem which is define some governing equation which is driven by some governing equation, or at the same time some boundary interaction is there. So, that kind of problem we can put the weighted residue technique and the different matrix form we can form. Now, in more details, one particular element, what are the different elements, that means this matrix can be formed, that will show in the next class. So, thank you very much for your kind attention.